Here's page 4 of Vector's addendum. On page 427 reading, we talk about the direction of the cross product result. And as we saw in the previous section, I vector cross j vector gives you k vector, and j vector cross I vector gives you negative k vector. Okay? And there's this convention called the right-hand rule, where you can actually use your right hand to figure out where the resultant vector is going to go. Okay, and this is assuming that you're familiar with three-dimensional graphing, which we haven't had a lot of experience with. But basically, when you do three-dimensional graphing, the convention is to make the x vector stick out towards you. The y vector kind of goes to the right side, and the z vector goes up. Okay, and so if you follow that, that's basically what they drew here, right? X, Y, and then Z goes up. So if you draw that convention, you can see that if you use your hand to first point in the X direction and then bend your fingers in the Y direction, then your thumb is actually pointing in the Z direction, right? So you can use your right hand to figure out which direction the cross product is going to go. All right, and I'll show you in class so that you can see it live, but it's kind of hard to see using this diagram. But basically, this is X, this is Y, and this is Z. Okay, or Z is actually X cross Y, right? Okay. All right, so that's the right-hand rule. And then this equation here, we saw from the formula sheet, right? And basically this can be derived from the determinant convention that we've been using so that we don't have to memorize this mess here. But, it's on the formula sheet, so on the exams you don't have to memorize anything. Basically, this part of it here, we're trying to figure out what the length of the cross product is, okay? And of course, the length of any vector can be found using Pythagorean's theorem, and that's what we're going to do here. We're going to take the top element, the middle element, and the bottom element, and we're going to put them in this equation, square them, add them together, and take the square root. And that gives us this big expression here, which is a big mess, isn't it? Now, usually the way you would figure out the length of a cross product is to use a formula which is the magnitude of vector A times the magnitude of vector B and multiply times the sine of the angle between them. And this should look familiar to you. When we did scalar product, remember, we had a similar formula, but instead of magnitude of A, magnitude of B, sine theta, we had magnitude of A, magnitude of B, cosine theta. So you can see the cross product and scalar product kind of like have a relationship in terms of, which component is kept and which is thrown away. So like cross products, kind of like the components that are perpendicular to each other are multiplied times each other. Scalar product, the components that are parallel to each other are multiplied times each other, okay? And so the proof of this is kind of a big mess. It's in the book, it's about 8 steps, and, it's not really something that you would figure on doing, but like the first step is that they say, okay, I'm going to look at this expression squared. When I do that, I'm going to have A magnitude squared, B magnitude squared, and sine squared theta, right? And then what they do is they say, okay, what a mess, huh? Let me rewrite that. Okay, and then what they do is they say, well, sine squared theta, I'm going to substitute in for sine squared theta 1 minus cosine squared theta, right? Because of Pythagorean's theorem, sine squared plus cosine squared equals 1, right? So they're going to do this substitution here, and you're saying, well, why the heck would they do that? Well, the reason why is they're going to sneak in cosine theta in here, and then that'll allow them to use scalar product later, okay? So the first step basically is to say, hey, I'm going to square everything, and you had to be a genius to think of this, but since since we're not geniuses, we'll just look in the book and we'll see, oh, the strategy is to square it first. Once I square it, then I can substitute in sine squared. I can substitute in 1 minus cosine squared. And then when I start expanding this and expanding this, then I'll see that eventually I'll get something with a scalar product in it, and that's going to help me figure out that these two are equal to each other. Okay? All right. So I don't expect you to know the proof, but the important first step of the proof is this. Okay? If A and B are non-zero vectors, then A cross product B is equal to 0. Then A is parallel to B. Okay. So you know how in scalar product, when we get A scalar product B is equal to 0, that told us that the two vectors were perpendicular to each other. And when we get A cross product B equals 0, that means that the two vectors are parallel to each other. All right. 2, consider vectors A and B. And first it wants us to find A dot B and A cross B. Okay, so let's find A dot B first. So A dot B is basically going to be 2 plus 0 plus negative 3. So that would be negative 1. So the answer to A dot B is negative 1. A cross B, not so easy. We're going to have to write this out here. We're going to have 2, negative 1, 3. And we're going to have 1, 0, negative 1. And first we're going to cover the I, and then we're going to get positive 1 minus 0. So it's going to be 1I. And then we're going to cover up J, and we're going to get negative 2 minus 3, which is negative 5J. And then we're going to cover up K, and then we're going to get 0 minus a negative 1, which is 0 plus 1, which is 1. So one mistake here. Again, the middle element needs to be subtract. So actually, instead of minus 5, it would be plus 5. So our final answer would be 1, 5, 1 is the cross product of A and B. Now let's do B. It says to find the cosine of theta using A dot B equals magnitude of A times magnitude of B cosine theta. Okay, well first of all we need to figure out the magnitude of A and the magnitude of B. Magnitude of A would be square root of 4 plus 1 plus 9, which is square root of 14, right? The magnitude of 1, 0, negative 1 would be square root of 2. Okay, so let's do B. It says to set up this equation, and we're going to have A dot B is negative 1, and magnitude of A is square root of 14, magnitude of B is square root of 2, and then cosine of theta is unknown. So you can see that cosine of theta we could figure out is actually negative 1 over the square root of 28, right? Okay. And then it says part C, find sine theta using sine squared plus cosine squared theta equals 1. Well, we know that cosine squared, or cosine is negative 1 over square root of 28, so we could rewrite the equation sine squared plus cosine squared equals 1. We could write sine squared theta plus 1 over 28, which would be cosine squared, equals 1. So sine squared theta is equal to 1 minus 1 over 28, which is 27 over 28. So sine theta is equal to square root of 27 over square root of 28. Now last part, we're going to find sine theta using this equation. So first thing is the magnitude of A cross B. So A cross B is 1, 5, 1. So the magnitude of A cross B will be 1 squared plus 5 squared plus 1 squared, which would be 27, square root. Okay, so it would be square root of 27. So we have square root of 27 equals magnitude of A is square root of 14, magnitude of B is square root of 2, so it's square root of 28, right? And then we have sine theta. Now we're going to solve for sine theta to figure out what sine theta is equal to, and we find out it's equal to square root of 27 over square root of 28. So all we did was confirmed in two different ways that the sine of theta is equal to square root of 27 over 28. All right? But you can see that it was, maybe easier to do it using scalar product and then using the identity sine squared plus cosine squared equals 1. All right, number 4. Consider the points A and B. Find OA and OB, OA cross OB, and then the magnitude of OA cross OB, and then explain why the triangle OAB is, the area of the triangle OAB is blah, blah, blah. Okay, so first, this is very, even if you don't understand where we're going, it tells you all the steps, so not too bad. So OA, vector OA, we're going to find by taking the coordinates, let's see, of A, and just putting them vertically, like in a vector form. OB, similarly, is going to be -1, 1, 2. And what about OA cross OB? Well, we know how to do that by now, right? 2, 3, -1. -1, 1, 2. And first thing we're going to do is we're going to I, and we're going to get 6 minus -1, which is 6 plus 1, which is 7, so 7I. Then we cover up the middle one, and we get 4 minus 1, which is 3, but it's -3 because we're doing the middle one is always going to be minus. And then we're going to cover up K, and we're going to get 2 minus a -3, which is 2 plus 3, which is 5K. Okay, now we want to do OA cross OB. We did OA cross OB, and now we want to take the magnitude of OA cross OB. So the magnitude of the vector 7, -3, 5 is equal to the square root of 49 plus 9 plus 25, which is 74 plus 9, which is square root of 83. Okay. And last of all, it says explain why the triangle OAB is 1/2 of that. Okay, so it says that the area of this triangle is going to be square root of 83 divided by 2. Well, we could confirm using the trig method that we know of. We know that the area of the triangle is equal to 1/2 AB cosine, AB sine c. Do you remember that? So we could use that formula, and we know that, A is actually vector OA magnitude, and B is actually vector OB magnitude. And the sine of C would be the angle between them, which would be sine of theta. Okay, so that is the definition of the cross product between the vectors times 1/2, right? And basically all we did was we took, to find the area here, we found the cross product and divided by 1/2. Okay, so that confirms the formula that we've always used to find the area of a triangle using two sides that are not right angles to each other.